scientific presentations given by leading Italian scientists in the world who contributed greatly to the advancement of knowledge and to the advancement of latest technologies. I want to also thank a lot for this opportunity the organizers of this event, Andrea Giuffrida, the president of Texas Scientific Italian Community, the two souls of this big event, which are Vincenzo Arcobelli and Antonio Cenini. Really, I want to thank them gratefully. And then also the other members of the scientific committee, that is Timoteo Carletti, Simone Napoletano, and Mustafa Tlidi, because together with them we selected among the many, many examples that the Italian excellence is providing in the world, the presentations that will be given today. The session will be divided in several subsessions, thematic subsessions, and we start with aerospace. It's my pleasure to introduce the first speaker, who is Professor Adriano Ghedina. Professor Adriano Ghedina is the director of the Italian Telescopio Nazionale Galileo, and the telescope is a very large telescope who is in the top of the island of San Miguel de la Palma in Spain. It is the most important telescopic instrument, optical instrument for the Italian astronomical community. And so it's my pleasure to introduce him, and he will speak us about the importance of the contribution of the Italian Telescopio Nazionale Galileo to the exoplanetary research. Professor Ghedina, the floor is yours for 10 minutes.
Thank you, Stefano. Thank you for the invitation. I hope you can see my presentation. Can you confirm?
Yes, we do. Yes, we do.
So I start right now. Thanks for the presentation. Telescopio Nazionale Galileo is an Italian infrastructure owned by Italian Institute of Astrophysics, INAF, and is sited in the island of La Palma, just in Canary Islands, just outside Africa, because of the wonderful sky that we have in the island. It's funded with the Ministero Universitario della Ricerca Italiano, but the legal framework into which we have to move to have maintenance administration is a Canary Island Foundation non-profit, and we have a staff of 32 people. TNG was inaugurated in '96, is a 4-meter class telescope, and we have several instruments installed at the COSAI. The access to observing time is through semestral call, where both Italian and international, and we have a pressure factor of roughly 2, I recall. In 2012, we had the international agreement with Switzerland, UK, and USA to install a specific instrument dedicated to research and characterization of exoplanets. Is a high-resolution spectrograph, and I will explain later how what it is. Ultra stable and ultra precise. And then in 2016, with the Premiale funds, we were able to install another high-resolution spectrograph working in the near infrared. And they can work simultaneously, and this is the only facility in the world that can extract simultaneously a high-resolution spectrograph, a spectrum from the visible to the infrared for an astronomical object. A spectrograph is a system, as you can see, the colored line in the middle of the slide, is a system that can decompose the light of the object that you are observing into its wavelength. And typically, any star, like our sun, has a continuum colored line with several missing parts, missing wavelength, due to the chemical composition of the sun. It's like a DNA of the object that you are observing. And in this case, HARPS is measuring the movement of this line with respect to a stationary framework. With this instrument, we have been able to start international collaboration for the research of exoplanets, create large programs of observation, and at the end, almost 2/3 of the time of the telescope is dedicated to planetary research. So how do you search for an exoplanet? For the bigger one, you can do direct imaging, but the typical way of search for exoplanet is through transit. That is, you observe a star, and through time, the light of the star gets dimmer and then back to its normal value. So you suspect that a planet has passed in front of the star, between you and the star. So there have been several satellites, both from the United States and from ESA, and the collaboration between them. And the next big mission of ESA will be Plato and Ariel, dedicated to observation of stars and the search for this light dimming. And thanks to this technique, there have been many interesting targets, and nearly 60,000 exoplanets confirmed. But to confirm an exoplanet, you need observation from ground. And this is what Telescopio Nazionale Galileo is able to do. You need to use the system of radial velocity. You have to imagine the system of star and planet orbiting one around each other. And it's like a seesaw in a kindergarten. So depending on the weight of the planet, the center of gravity, the balance point between star and planet will move away from the star and close to the planet. So imagine this planet orbiting around the star, around the center of gravity, will introduce an effect on the star, a wiggle, a movement, which is produce the star getting closer and far away from us. And this effect, which is also known as a Doppler effect, will move the spectrum, the spectrum line, with respect to us and with respect to the reference frame. So what HARPS do and what the Galileo does is to measure the movement of this line. And with this system, it has been discovered 30 years ago, not by Galileo, but with another telescope, the first exoplanet orbiting a star similar to the Sun. This was in 95, and this began the tender of searching for exoplanet. This was a very huge planet. It's the radial velocity of 50 meters per second is like 10 times the mass of Jupiter. If, as we want to search for an Earth-like planet around a Sun-like star, we have to get down to 10 centimeters per second precision. And we are able to do it, but I will show you what happens. Thanks to this 6,000 exoplanets, we have discovered that there are not only the planets that we have in our solar system. There are several kinds of planets. For example, we have super Jupiter or gas giants, which are several times the mass of Jupiter, or there are super Earth, rocky planets, 2 or 3 times the size of Earth, but made of rock and several times the mass. We also have sub-Neptunes, which is a kind of a planet made of gas, smaller than our Neptune, that we didn't know that could exist. And you know that when you discover new things, you have to make new theories and try to explain what you are observing. And also we found that the range of the temperature in this planet is vastly changing from icy cold to a planet made of melted iron that could have rains of lava and rains of iron on the planet. We also have water wars in some cases. So you see there are many kinds of planets that we didn't know could exist, but also there are several solar system composition, solar system exoplanetary configuration You see in the lower right, we have ordered system that, I mean, in our decision is to have the rocky planets close to the star and gaseous planet like Jupiter and Saturn far away. But we also have found that there are anti-ordered, where you have the gas giant close to the star. You have system with all the planets that they are all the same, and then you have mixed. So we have to think about how planetary system forms from the protoplanetary disk, the gas that condenses and form the planetary system. Is not as how we suppose it could be, but we have to think about new theories. And if you want to search for an Earth-like planet, you have to think also about life and habitable zone. The habitable zone is the distance from the star where the water is liquid, is not too close when the water can get to vapor, nor ice. And this distance strongly depends on the kind of star that you are looking for. The sun is like in our case, but if you look at the TRAPPIST system, which is a system of 7 planets that we have discovered around a very cold star, you see that the whole system with the 7 planets is well within the orbit of Mercury, very close to the star, and so the habitable zone changes correspondingly. So what did we learn? We learned that there are several kinds of planets. We have several kinds of temperature and condition and the composition of the planets. The planetary system also have many differences, not as we thought it could be. And we also can measure orbital eccentricity, and we have seen that there is history of migration of planets that forms far from the star and then get closer. And when they get closer, they lose the atmosphere. So the limit in all of this is not the precision of the instrument, because with HARPS we have shown that we can get to much better than what we could we would need to search for an Earth exoplanet. But you have to consider that the star is a sphere of gas, which has pulsation, it has spots, it has magnetic fields, and this produces noise that we have to disentangle from the effect of the planet on the star. So it's a tricky research, but we can do. And also, you have to think that when the planet passes in front of the star, between us and the star, the light of the star is contaminated, is polluted, is altered. It gets the imprint of the atmosphere composition of the planet. So we don't see the planet, we just see the effect of the planet on the light that we receive from the star. And we can study the atmosphere of the planet, and in this case, the help of James Webb telescope is fundamental because of the precision that it gets. But you understand that we can know the atmosphere and the composition. We have discovered water in the atmosphere of exoplanet, CO2, methane, and many other components. And also, we have a star very close, which is the sun. So with HARPS...
sorry, Adriano, if I interrupt you, but we are
almost
running
finished.
out of time.
Almost finished. Last slide. Okay, this and the conclusion. Just we are saving the sun 24 hours. I mean, during the day. So HARPS works 24 hours, and we can disentangle, see the effects of the stellar activity over the lights that we receive from the sun. So I get you to the conclusion that the TNG allows the international community to have access to the best instrumentation for exoplanetary research. And I leave you with this sentence from Giordano Bruno, who was not the first, but one of many philosophers who thought that we were not alone in the universe. Thank you for the invitation, and thank you again. Sorry for being late.
Many thanks, Adriano, for your beautiful presentation. And the next speaker is Professor Cesare Grava, who is a lead scientist at the Southwest Research Institute, NASA Solar System Ambassador based in San Antonio in Texas. And the Institute operates a very large space science and engineering program, which is actually home to principal investigators for all major and NASA missions. And therefore, we are very happy to have Professor Grava with us, and he will tell us about the UV spectrograph lamp on NASA Lunar Reconnaissance Orbiter, studying the moon with ultraviolet eyes. Please, Professor Grava, the floor is yours for 10 minutes.
Thank you very much. Hi, good morning, or good afternoon, good evening, wherever you are in the world. It's an honor for me to be here talking about the UV science done on the moon. And I want to thank you again for inviting me. And what a perfect timing it is, because the TNG telescope is the first telescope I used when I was a graduate student at the University of Padua. So I have fond memories about that. And the next speaker is studied with me at the University of Padua. So it's a great connection. So my name is Cesare Grava. I am a lead scientist at the Southwest Research Institute. And I just have to find the sharing the screen here. Okay. I hope you can see the presentation. Are you seeing the presentation or the? Oh, wait a minute.
Yes. Okay. We can see your presentation.
Okay, so okay, I hope this is okay. Okay, so I am based in San Antonio, Texas. I'm a lead scientist, and also I'm the 2025 NASA Solar System Ambassador to promote NASA mission achievements in the world. And I've been here for a little more than 12 years, and I study exospheres in the solar system. So the moon in the solar system, okay, in the ultraviolet, how it is studied. So this is a view of the moon, as you will see, with your own eyes. So you got the visible light, and you see this beautiful satellite. The box in red includes all the near side, so the face you are always seeing for the Earth, with the familiar dichotomy between the dark Maria, which is not Maria's Maria, is Latin plural for mare, which is sea, so seas, which are ancient lava lakes, seas of lavas. These are darker, whereas the highlands, especially mostly found on the far side, are bright. And so you can see here some craters, famous craters, Tycho, Aristarchus, Copernicus. So this is what you see from your eye. So if you had a pair of UV goggles, how would you see the moon? Well, we have this instrument, a lamp, to tell you. Okay. So, okay, this is how it looks. So pretty different. So if I blink back and forth, you can see there's an opposite contrast. So now the Maria are brighter and the highlands are darker. And that's because of how the light, the surface of the moon interacts with the photons of the sun of different energy wavelength. So UV photos are a little bit more energetic than the visible one. And so these are great. So this wavelength is great to highlight pyroclastic deposits, craters, also crater rays, which are more easily visible. So how do we do that? We do that with a spectrograph called the lamp. So a spectrograph is like the instrument that Adriano was saying before, is instrument that collects light over a wavelength. In this case, it's a extreme ultraviolet and far ultraviolet, so very short wavelength. And it's disperses over our range of wavelengths. It is, so you can see a picture here. It's about a shoe box size instrument. It is it's been aboard the Lunar Reconnaissance Orbiter, or LRO, which is NASA's premium assets on the moon. It's been orbiting the moon in polar orbit since 2009. So it's a polar orbit. It means that it is orbiting not in the equatorial plane, but in the polar orbit. So this instrument can observe both the lunar day side and the lunar night side in the ultraviolet wavelength. And the goals are to study the composition and the physical properties of the lunar surface and also the lunar tenuous atmosphere called the exosphere. So how do we do that? So we use three sources of light with lamp. So the first one is, of course, the sun. And the sun is a big emitter. It's the primary source of UV light in ultraviolet as well, like in the visible. And we use the sun to illuminate the lunar day side and take measurements on the day side. And also we use the interplanetary medium, which is, or interstellar medium. So this is material that comes from outside the heliosphere here, very far away. So this is our solar system for comparison. And so interstellar material, which passes through our own solar system as neutral, so mostly hydrogen and helium, and they glow because they scatter the light from the sun in ultraviolet. And so if you could see the sky with a pair of UV goggles, you will see a diffuse glow all around you. And the third one, we use the UV bright stars. So stars of spectral type O, B, and A, they are particularly bright in the ultraviolet. Of course, this is a picture of a galaxy, but the stars we're using are all in our own galaxy, Milky Way. And so these two sources allows us to study the lunar night side, where the sun doesn't shine, of course, but also areas on the polar regions where, especially areas at the bottom of the craters in the polar regions, they never receive direct sunlight. They are in permanent shadow. It's called the permanently shaded regions. And they are among the coldest places in the solar system, as cold as like a 20 degrees Kelvin, which is very, very low. So 20 degrees above the minimum, the zero absolute. And so this is an innovative technique. Nobody has done before. And basically as the spacecraft orbits, the LAMP instrument takes a measurement, a spectrum of the lunar surface in push-pull mode. And it's an instrument that has been designed a bit here in San Antonio and has been orbiting the moon since 2009. Okay, so let me get you some science results. So what we can do with the ultraviolet wavelet on the moon. First of all, there's lunar hydration. You might be familiar with the concept that the moon is not dry, so it has a little bit of water around. We are talking about really a monolayer of water molecules, but this instrument can detect this hydration. On the left, you see a measurement of the water abundance on the moon. As you can see, so wet here is in the top. So you can see how the water changes, the hydration changes. So it is pretty dry at noon, and it recovers the lunar water. Okay, the water on the surface recovers at dusk and dawn. And of course, you have more water, a little bit more water at the latitudes towards the poles. So this we use the light from the sun to take these measurements. And also with the light from the stars and the interplanetary medium, we can study the hydration in these dark regions. This is the south pole of the moon, and you can see that the distribution of water ice, the blue points, is uneven in the south pole. So these are, for example, 3 famous craters near the south pole of the moon. They all have different distribution of water. So this Haworth is pretty, has more water than Shoemaker, and yet they are very close together. And it's an area of active research right now. So why this distribution is uneven. The exosphere is what I most familiar. I am been studying the exospheres for more than a decade now. Exosphere is the term we use for the very tenuous atmosphere. So it's a collisionless environment about the surface of the moon. And we can study with this instrument the correlation between the helium in the exosphere of the moon and the solar wind. So the solar wind is a main contributor to the helium exosphere. And so you can see when the spacecraft goes with the moon enters the Earth magnetotail, then our own planet, our own magnetosphere, shields the moon from the solar wind. So basically you switched off the solar wind and you can see that the helium in the exosphere decreases and then recovers when we exit the magnetotail. And also correlating this measurement of helium with the alpha particles measurement from other spacecraft, we found a correlation with the solar wind, which is not one-to-one. So we found an additional population of helium atoms on the moon that we think come from the gassing from the lunar crust, from the interior of this helium and other radiogenic elements. And so I'll leave you with this movie here. There are many other scientific results that I don't have the time to go through. This was the measurement taken from just after LRO was launched. And so this is a cross experiment. So they launched the upper stage of the booster, that rocket that brought LRO on orbit on the moon in permanent shaded regions. And this instrument, LAMP, was looking at the sky, waiting for the cloud of debris, the plume, to measure. And so with the spectrum, we were able to detect carbon monoxide, molecular hydrogen, mercury, calcium, and magnesium in this coldest region of Cabeus. So it's a very complete instrument that allows you to do many measurements. So mineralogy, polar volatiles, and exosphere, and many others. And okay, I'll leave it to my conclusion. So UV spectroscopy is now recognized as a powerful tool to study multiple processes in the solar system. Space weathering of surfaces, distribution of volatiles, and also the source rate of the exosphere, and also the loss rate. And LAMP is together with other 6 instruments on NASA Lunar Reconnaissance Orbiter, and now they have been providing key measurements in lunar exploration since 2009. Especially now with the Artemis program, is a key asset to plan robotic and crewed missions. Thank you very much for your attention.
Thank you very much to Cesare for the beautiful presentation. And now we move to the last speaker of this session, who's coming from Chile, Professor Claudia Palladini. She is Associate Astronomer, Deputy Head of the Office for Science at the European Southern Observatory, and she's Vice President of the European Interferometry Initiative. This initiative is an open association of institutes and labs willing to collaborate in the exploitation and development of optical long baseline interferometry in optical infrared astronomy. And it's funded by several programs of the European Union. Actually, the project has received funding from the European Union's Horizon 2020 Research and Innovation Program. Claudia will speak to us about his journey from Salento to the Andes, a story of giants, stars, and telescopes. You have 10 minutes.
Hello from Chile. Feels a bit like the Eurovision. I have the sun that is rising behind the Andes next to me here. I'm very happy to be here with you. And since I have a very short time, I will just dig directly into my presentation and take you through this kind of symbolic journey. We saw before the moon, I will take you to Mars, or to a place on Earth that looks very much like Mars. So I decided in this presentation to take you with me really in this symbolic journey, and to explain you basically what is the job of a staff astronomer working at the European Southern Observatory. I am originally from the south of Italy, from Leverano, a small town close to Lecce, and I had European training. So I studied in Padua, like my former colleague Cesare that was our speaker before, but then I had a PhD in Vienna, and I spent some time as a postdoc in Brussels. And since 2017, I am based in Chile at the frontier of ground-based astronomy. And in my work, I move between research, training of the new generation, and also shaping a bit the European collaborations at European, but not only level in astronomy. A few words about the European Southern Observatory. Many people of you are familiar with NASA. Well, there is the European Agency for the Space, which is the ESA, and the European Southern Observatory is the analog, but for the ground telescope. It is an organization, intergovernmental organization made of 16 countries around Europe, including Italy. Italy joined actually in 1982. And additionally, there are also the hosting country where the telescopes are located, which is Chile, and a strategic partner, which is Australia. Our mandate at ESO is to design, build, and operate the world's most advanced ground-based astronomical telescope that enable cutting-edge discoveries. And we also want to foster international collaboration in astronomy. I work for about 105 nights per year, so which is about almost 70% of my time on a remote mountain top in the middle of the Atacama Desert. And looking at this picture, you can understand why I was speaking about Mars, because it really looks, if one imagines it like Mars, it's really a desert. There is nothing around. We are at 2,600 meters above the sea level, and we spend there up to 2 weeks per month. There are 4 8-meter telescopes on the mountaintop, plus 4 1.8 movable telescopes. You know, there are some people that in the morning work around their dogs, and there are some others, like our engineers, that work around the telescopes. And then there are 2 surveys. One of them is actually operated by the Italian INAF. Thanks to this large telescope, we have unparalleled image resolution, and we enable scientific research and scientific discoveries, like, for example, the 2020 Nobel Prize for the discovery of the supermassive black hole at the center of our galaxy, which was obtained also thanks to one of the instruments that I operate, which is the instrument gravity. And I'm very excited to tell you that we were observing this like last week. But beside doing enabling, doing service to the community, enabling science around Europe and not only. I am also interested in scientific research myself. I'm part of the community. And in particular, I am been always very motivated by the statement by Carl Sagan originally, but also Marguerite Hack, which is, we are all made of star stuff. And that's exactly what I work on. My scientific focus is about studying giant stars in the sky. I study stars which are, most of the stars, if you look at the sky, that you can see with your naked eye. So these are giant stars, the future of our sun, that now are kind of 100 times larger than the sun. And what I try to understand when I do research is how the material that is built during the lifetime of the star then returns to the cosmos. Basically, I study the surface structure, the stellar wind, and how these elements are then that are produced during the internal of the stars are then returned to the interstellar medium, become then the future generation, building blocks for future generation stars and planets. And you can see here in the background one of the stars that we have been observing over the last years. And you can see it resolved. This is a real image actually, and you can see it resolved, like you see resolved basically our sun. I told you about giants on the ground, stars, telescopes. Sometimes observing stars and objects in the sky with one telescope is not enough. And in fact, even with the largest telescopes, most of the objects that we observe in the sky will still remain as point source. And we use a special technique which is called optical interferometry, where we observe these objects to be able to resolve them with several telescopes at the same time. And then it's kind of like observing this object with a telescope which has a virtual diameter, which is the distance between these two telescopes, for example. So if I have two telescopes that are 140 meters or 200 meters, like it's the maximum we have on the mountain right now, apart, then it's like observing with the telescope which has a virtual diameter of 200 meters. Just to give you an example, the details that we can observe in this case, it's like looking at the soccer ball on the moon. So these are the kind of detail, but we are limited with this technique to objects that are the most brilliant one. And so my expertise is really to turn this complex technique into breakthrough science and to obtain images like the one that I just showed you. And I'm also engaged, as it was mentioned at the beginning in my presentation, in the sharing this knowledge of this very special technique around Europe and around the world. And actually, I was vice president until last week, but I was recently elected this week as president of the European Interferometry Initiative. And we engage really into sharing the knowledge with the new generation for this technique. But this mandate is also to train the new generation of scientists. And so then it's like doing this job is like wearing many hats in astronomy. We are leading at the forefront of scientific research. We are enabler of science, thanks to the discoveries that are done at the observatory where we work at, operations. But we also support growth through mentoring and training. And I am currently the line manager for students and fellows at the observatory, and there are a lot of Italian astronomers that work with us. In particular, we are a small department, but we have like 4 Italian fellows that recently joined us. And something interesting that maybe you can discuss or you can think about, many of these astronomers come from institutes around Europe. They don't come directly from Italy. So this is something that we should think about, why the Italians don't go directly to South America, to this place, which is the most interesting, I think, for where we are at the frontier of astronomy. So they have first to go to some other institutes. Are they afraid of traveling? I don't know. So I want to, since we are talking about Italy and Italian researchers, I want to share my personal feeling of Italian touch. So what being Italian brings to my work, I think resilience, creativity, and curiosity is what, which is deeply rooted into our culture, have guided me through this scientific journey. But I think the journey itself is a fundamental part of who I became. And so I would like to leave a message to the young generation. They should not be afraid of traveling and stepping outside of their door. Going back to the giants, I want to leave you with this slide, which is the new big scientific project that we are building. It's the European Extremely Large Telescope. It's a telescope with the 39.2 mirror, segmented mirror that is currently being built in the mountain in front of Paranal, where I work, and it will be operated from Paranal. Italy has a very big contribution to it, both from the technological point of view, from the part of the as a industry. It built the dome. It plays a key role on the segmented mirrors, but also in instrumentation with enough. With key roles in Mikado, Maori, and the telescope will see the first light in 2028. So there are excitement at the horizon, and for new scientific discoveries. And I hope that we will meet soon and speak also about this. Thanks a lot. Ciao.
Thank you a lot. Thank you, Claudia, for the beautiful presentation, and thanks to all the speakers of this session. We move now to the next session, which is about presentations on basic and applied science. And I call on the floor the two moderators, Timoteo Carletti and Simone Napolitano. Timoteo is a professor at Namur Institute for Complex Systems here at the Université de Namur in Belgium. And Simone is also works at the Polymer and Soft Matter Dynamics Group, Université Libre de Bruxelles in Belgium, and they will be the moderators of the next session.
Okay, first of all, it's a very big honor and a deep emotion to be here talking, and thank you very much for the invitation. I will be presenting a line of work that is profoundly multidisciplinary. And the idea is that somehow neuroscience and engineering can inspire each other. Okay. So the starting idea is to study side by side the notion of designing, which is the core of engineering as it was always done and as it is today, and the idea of emergence, which is how nature creates things, how nature gets complexity, how nature solves problems. And we go back to a very old question and a statement which is now obvious. The brain is totally unlike a digital computer. Of course we know it, but it's a little bit more interesting if we start asking why. In engineering, computation happens by design. Architectures are fixed. There is little or no redundancy in the elements, and we need very high reliability because noise and errors, etc., are a bad thing. But from what we know of our brain, and particularly in the last decades, we really learned a lot about our brain. Strikingly, we understand it's practically the opposite. It's the opposite because the a priori design is limited to some structural aspects, but is mainly emergent, self-organized, and not only it tolerates noise, but it uses noise, and it uses mistakes, and it uses failures. So the question is there any way in which we can get inspiration from neuroscience to design electronics in a new way? And I want to clarify one thing here. When I say new way, what I mean is not some exotic or complicated type of electronics, not at all, as you will see. Using very basic, very simple and fundamental electronics, but in a new way. So we know, for example, that if we take neural networks, such as deep learning neural networks, they don't really have intrinsic activity. They can do very complex things, but they project inputs to outputs. That's completely different from what we have in a brain, where 80% of the activity is spontaneous or in a way, we could consider it noise-like. So it's clear there are deep architectural differences. And for example, if we put side by side a GPU, a single GPU card, and a brain, we notice that a GPU consumes 10 times as much. Now that's quite incredible because with a single GPU, you can run some fairly simple AI models, but you can't really do that much. So obviously there are profound architectural differences, which have to do with the fact that one is biological, the other one is not, but actually they are more profound than that. Now, in part, this has to do with the network organization. So with the fact that currently in the way we design, we use very regular structures, but nature is able to generate and harvest very high complexity networks. And in the case of our brain, we have different aspects of connectivity. We not only have one design. The design, the structural connections, the wires between different parts of our brain at all the scales, they are only a starting point. We then have like a continuous symphony of interactions that are largely uncoupled from this connectivity. So the question is, can we reproduce this electronically? And that is what I set out to do. And one key concept here is the notion of emergence. So the formation of shape, the formation of structure, the formation of scaling laws seemingly out of nowhere. And in particular situations where the whole, such as a flock of birds or emergent cognitive activity, has properties that are completely absent in the individual parts. The question is, can we actually get this with the electronics that we have today without disturbing any exotic, any very complicated technologies, and actually potentially unlocking a huge computational ability with very little investment? And that is what I have been working on. I skip a few slides. I want to show you this circuit that will make all of you smile because it is desperately simple and desperately outdated. This is the first circuit on which I worked more than a decade ago, and it is a very basic electronic oscillator. However, when you start looking at the behavior, you will start becoming more curious. Because as we change one of the parameters, for example, the applied voltage, we can see that this circuit generates a wealth of possible activities. Absolutely, it is not just something that generates a periodic signal, it generates very complex activity. And as you see on the left of this slide, those are instead biological recordings from postsynaptic potentials. And we can see, at least qualitatively, that there is some similarity. Oh wow, did I make an electronic neuron? Of course not. This has nothing to do with neurons. The structure has nothing to do, the complexity is orders of magnitude below, but that's precisely the point. The point is that some of these phenomena are universal. And under the correct circumstances, we can get them in very simple electronic circuits. The problem is, we are orphans of a theory. We don't have the theory to synthesize and to design such circuits. Some work that I did involves trying to create what I would call a numerical serendipity. So using a kind of genetic algorithm-like approach to discover new circuits. And we discover entire classes of new circuits which are there, waiting to be found, showing that they are nothing special, simply we didn't know them because nobody looked for them before. And we can enrich them, creating fractals and capturing different interesting aspects of activity. But I would like now to go to what happens when we put them together. Now, we are interested in networks. Everybody's interested in networks nowadays. But what I find interesting is the phenomenon, remember what I said before, by which complex structures appear seemingly out of nowhere. So here we have another very simple experiment, and I choose them on purpose, where we have a ring. And a ring is one of the simplest structures that you can imagine. But if you look, this ring likes to self-organize in communities, groups of nodes that for some seemingly arbitrary reason like to synchronize while repelling others. Now, some key properties of this phenomenon are very similar between what we observe in brains and in this kind of circuits. Anything special about this circuit? Of course not. And that is exactly the point, that we have all these phenomena that are accessible with very, very little. Now, I spare you the details. We can find a lot of additional phenomena using more complicated hardware, but I want to jump to some possible applications. Now, one interesting application is creating what we call toy models. A toy model is a brutally simplified model of some physical reality, such as a brain. And here is a very, very simple model of brain connectivity that captures some observations that we have using functional MRI. The interesting thing is that this model is very simple to manipulate, to damage, and to study. But critically, it is much richer than what we would get from a purely numerical simulation. Because all these circuits, being physical, they are not ideal. They have defects, they have mismatches, etc., etc., etc. Now, possible applications also include creating advanced controllers for robots that can work without a single line of code. And that is something quite remarkable. And other applications include, for example, creating networks of sensors that may be dispersed over the environment. Here you see very simple circuit boards that can sense light intensity or moisture, and they interact together in ways that are inspired by what we learn from neuroscience. And accordingly, we can also create networks that can solve computational problems. You can see they are spiking like activity while having nothing to do, in fact, with a neuron in a strict sense. And now there is some of the work that I'm doing in China that has to do with getting some biomarkers from this. Last but not least, there is also a cultural dimension to this that has been explored by many people, that these kind of circuits generate incredibly rich and graphically beautiful dynamics. Thank you very much for this opportunity and for your attention.
Thank you very much. Thank you very much, Ludovico. So the next speaker is online, is Riccardo Molo from the Institute of Science Tokyo in Japan.
Can you hear me?
Yeah. Can you put your slide on, Riccardo? Okay, good. You have 10 minutes.
Okay. So, first of all, thank you so much for the opportunity to speak at such an event. It is truly an honor to be part of it. So, yeah, I'm a postdoc at the Institute of Science Tokyo, that used to be the Tokyo Institute of Technology until a few months ago. And I'm also part of the Association of Italian Researchers in Japan. So if you want to get in touch with the community of the Italian community in Japan, please reach out through this association. And since this is an event of Italians in the world, I would like to speak 30 seconds about this outreach project called Penna Amiche della Scienza, in which we match an Italian scientist with elementary school or middle school class, and there is a monthly correspondence. And this was funded by Valentina Borghesani, who is another Italian researcher in the world. And we have members, well, from Italy, of course, researchers in Italy, but all over the world, except for Oceania, we are in every continent. So this is also a nice way to keep in touch with the Italian community and also to give back through this outreach project to our country. So I invite you to check it out. So today I will talk to you about a story that starts in the 17th century and arrives until our days, and it's about the study of synchronization. So I will briefly introduce what is synchronization, and in particular this very powerful technique called phase reduction that was mainly developed here in Japan, in particular by the group of Kuramoto, who is very famous for his Kuramoto model that I will briefly discuss, and then in the end, I will discuss some applications. Synchronization is a collective behavior that is observed in many natural and artificial and engineered systems, such as power grids, natural systems like in the heart or in frogs. And I think it's better to introduce it with an example. So if you put a hand on your chest, you will feel a heartbeat. But actually, this is the result of the synchronization between billions of myocardium cells that are firing, are releasing electricity altogether. But they are synchronized, and so you hear these periodic beats that it feels like it's a whole, but instead it's made of many cells. And similar phenomena happen also, for example, in some tropical fireflies that under certain conditions flash at the same time, or also in Japanese bullfrogs, and there are so many examples of it. And as far as we know, this phenomenon was described for the first time in the 17th century by the Dutch physicist Christian Huygens. The legend says that he was sick in bed and he realized that two pendulum clocks that he had in his room were synchronizing in antiphase, like in this figure. Actually, this is wrong, and he was trying to get a patent for high precision pendulum clocks, and he realized this phenomenon while working on his patent. But still, it was remarkable the way that he described completely this phenomenon, and he understood that the key to achieve this odd sympathy, as he called it, was the interaction between the two pendulum clocks that from now on I will represent as metronomes, because they're just simpler to find nicer pictures of metronomes. And so these two, let's say, things that oscillate, so oscillators, they are able to synchronize where they are interacting, and Huygens described this motion. Now, the metronome is a system that is very simple to describe. So it's something periodic. So if you have never seen a periodic behavior, it's kind of like that. So we have a function, so a behavior that repeats itself after a given amount of time, called the period. Of course, in nature, the systems are never perfectly periodic, but we can approximate them like that. And so when a system is so simple, it's very easy to describe. However, natural systems can be periodic but very complicated. So there are behaviors that are still periodic and quite difficult to describe. However, there is this technique that applies to any periodic system, no matter how complicated the behavior is, that is called phase reduction, and basically allows us to treat every complicated periodic system as if it were a metronome. So we have our heart, the cells of our heart, and we can treat them like metronomes. So no matter how complicated the system is, through this technique, that is an approximation but works very well, we are able to treat systems as if they were very simple oscillators, so metronomes. And through this technique, this guy here, Professor Kuramoto, who just was awarded the Boltzmann Medal, which is the highest recognition for statistical physics, 50 years ago discovered this model that now this is the only equation I will show, just to show you how simple it is. So this model allows to analytically, so pen and paper, to treat synchronization, to understand when a system synchronizes. So through this technique called phase reduction, we can take a very difficult system, make it in a form that is usually not as simple as this one, but fairly simple. And so we can study the synchronization of even very complicated system. And this is very important because it allows, based on the interactions between the oscillator, to know when we will have or not synchronization. Now, the simplest case of the Kuramoto model, the one that can be done with pen and paper, assumes that everybody is interacting to everybody. So a very simple interaction is called all-to-all or global coupling. However, real interactions are more complicated. And physicists, but not only, also mathematicians, engineers, have been studying, as we've seen in the slides of the presentation of Ludovico, have been studied networks. So how how systems interact, so interactions in real systems, and the Italian community has given a big contribution to this field. And so in this case, we consider the oscillators, so the metronomes, connected with more complex interactions. And actually, over the past few years, we have come to realize that interactions in real systems are even more complicated than network, because they are not just 2 by 2, but they are group interactions. And if you want to know more about it, there is this very nice perspective that came out a few years ago in Nature Physics. And also you can spot many Italian names, because also Italian researchers, some of which are abroad, gave a huge contribution to the field of higher order interactions. And actually 2 of those physicists are there with you, Stefano Boccaletti and Teo Carletti. And so in this case, we consider the interactions between the metronomes as taking place not only through links, but also through higher order interactions, to group interactions that dramatically shape the behavior and in particular the synchronization. And now these 2 examples are toy networks. So Ludovico introduced toy models. For toy networks is the same thing. So very, very simple basic networks, but of course, when we go to real world systems, they are much more complicated. And it's really important to know how these connections, so these interactions, shape the final behavior of the system, so synchronization or not synchronization, because there are systems where we want to achieve synchronization. The example is the heart. So we need the heart to be synchronized. So we need all these billions of cells to be synchronized. But in other systems, we don't want synchronization. For example, in the brain, where synchronization is associated to pathological states such as Parkinson or epilepsy. And so these techniques...
You have 1 minute.
Yeah,
1 minute.
Yeah, thank you. I'm almost done. So these techniques of synchronization, the study of synchronizations of network, this theoretical works study the synchronization in networks or in systems with higher order interactions. They are very theoretical, but they are fundamental for applications such as deep brain stimulation, when one is trying to desynchronize hypersynchronization in the brain. And so now in my group in Japan, I'm putting to use all the techniques that I learned about synchronization in networks and hypergraph, using this phase reduction technique that was developed in Japan. So with this, again, thank you so much for the opportunity, and I thank you for your attention.
So, Itamar, can you... I saw you previously online. Yeah, okay.
You have to unmute himself.
You have to unmute yourself and show your slide, please.
Unmute, okay.
Okay, good.
So now you hear me.
Yeah, we can see you. Can you put your slide on?
Yeah. Do you see them?
Not yet.
Okay, I need to share or what?
Yeah, to share, yeah.
So I'm sharing. Okay, so it's connecting, share content. Connecting. So you see me and you hear me, right?
Yeah.
So
Maybe there's on another display.
okay, connecting. It says connect. I say, allow. Allow. What do I need to do? Select window. It's protected. It says touch screen. Allow. Okay. All right. Now.
Okay.
You see that?
Yeah, you see. Thank you very much.
Okay,
Yeah,
thank
10
you.
minutes.
Okay, so I want to talk to you about the unexpected consequences of disorder in amorphous solids. And to this aim, I want to first introduce to those who don't know, I'm sure many do, what are amorphous solids. So amorphous solids are really a large, very large group of solids that don't have a long-range order in their atomic structure. That is to say, if you know the position of a few particles in a certain environment, you cannot predict the position of other particles far away, as you can do in ordered solids, in normal solids, like sodium chloride. There are many, many types of those, depending on the size of the particles involved. So from atomic sizes, you have metallic glasses and silicate glasses, the ones that you have in the window. You have polymer glasses, you have colloidal glasses, you have foams, you have emulsions, you have granular solids like sand, you have dense granular suspension like mayonnaise, and they all have in common the fact that there is disorder, and the disorder I want to show you has some very interesting, deep, and surprising consequences. So firstly, I want to show you a film, and in the film, it's a film by a commercial company who showed the special properties of metallic glasses. Metallic glasses are glasses that you make by combining in the melt 4 or 5 different metals and cooling rapidly so that it doesn't know on which lattice to sit. And then what you're going to see in this movie that maybe some of you have seen before, that we have 3 tubes, one with steel at the bottom, one with titanium, and the third one with a metallic glass, and we're dropping a steel ball.
We don't see the movie. Can you?
Here. Yeah, I first explain. So the stainless steel here, the titanium, and here you have they call it the liquid metal. It's a metallic glass. And now we throw a ball from above, and you see the one that fell on the metallic glass jumped out of the tube, whereas on the steel and on the titanium, there is a finite so-called restitution coefficient. Now, why is that? The reason for that is that in standard metals like steel, like titanium, there are defects. And when a ball like this hits the material, the defects move. It's called glide. And this is dissipative. It takes energy out of the falling ball. And therefore, the restitution coefficient is smaller, much smaller, or closer to 1. But for the metallic glass, it's huge. And the reason is that there are no defects in a metallic glass because there's no order in a metallic glass. So there's no order with respect to whom you can define a defect. So this is very interesting in the sense that the disorder, in a way that you may not have predicted, makes the system very elastic to small perturbations, much more elastic than standard metals. Now, the question that I want to show you, the issue that I want to show you, that there's interesting phase transitions within the solid phase. So first question that I want to raise is, when does a random collection of particles act as a solid? So this, you look at it. Is it a liquid or is it a disordered solid? Solid or liquid? Well, that question has already been raised in the 19th century by Mr. Maxwell. And Maxwell has discovered something very interesting. He discovered that when the particles are frictionless, when the average number of contacts between particles is 2D, i.e. 4 in 2 dimensions, 6 in 3 dimensions, then the particle jam. That is to say, they create a solid. They cannot flow. So this is a condition for a phase transition, if you want, from the disordered liquid to the disordered solid. They're both disordered, but there is a very interesting transition that has been studied a lot recently. It can occur also at 0 temperature. It's not a temperature-dependent transition because it's just a question of how many connections you have between these particles. So upon jamming, the pressure rises from 0 to final values. The jamming transition, as I say, was studied extensively over the last 2 decades, and a lot is known about critical exponents, about length scales, about divergence. Very interesting work had been done. I'm not giving you references because we have such a short time. Now, we have discovered in our own research a new and surprising transition within the jammed state. And to understand how this comes about, I want to say that before I told you that amorphous solids are elastic at small perturbations, but have a very plastic responses when strained more, and typically this is due to the creation of quadrupoles in the displacement field. That is to say, if you have an amorphous solid, you cannot have a monopole. You cannot have a region that is expanding, because this goes against the pressure and it will be pressed back. You also cannot make a dipole, because if you pull in a dipole direction, then in the orthogonal direction, the system will come inside, and therefore you get a quadrupole. You can never get a dipole. So technically, we say, like in electrostatics, where charges are protected, in elasticity theory, both monopoles and dipoles are protected, and the lowest order way to release stress locally is by creating a quadrupolar structure in the displacement field. So particles are moving out in two directions here and moving in these directions here. This is from a numerical simulation. This is a theory that we put up in order to fit this, and there's actually no distinction. We have an analytic formulation of these plastic events that are quadrupolar. Now, the lesson, therefore, is elasticity theory. Monopoles and dipoles cannot be created locally. They're excluded by topology. Now, when quadrupolar responses are distributed non-uniformly, that is to say, when there is many quadrupoles like this, but they're not uniform, then there is a gradient of them, and the gradient of them acts like a dipole, and this results in screening. And this is akin to the bi-screening in electrostatics. It was not known that this is the case, and in our work in the last 3-4 years, we have discovered that this screening exists also in elasticity and has many consequences that I'm not going to tell you everything. I'm just going to give you the general picture. So the general picture, you can see if you do a very simple experiment. And the experiment is you take an amorphous solid, this is green stuff, that is held within a circular either a ring or a sphere. It could be in 2 dimensions or in 3 dimensions. And in the middle, we have a little hole that we inflate. And we ask, what is the displacement field upon this inflation? Turns out that the result is totally different when you have a liquid, when you have a solid, let's say a high pressure solid. And what we discovered is that there is an intermediate phase between the elastic solid and the liquid, that you cannot go from elastic solid to liquid without going through this one. And the idea is this. So in the liquid, when you inflate inside, the influence of this is decaying exponentially. Decaying exponentially with a characteristic length scale, let's call it psi. And what psi is doing, psi is diverging when you come towards the jamming transition. So this has been studied, and we know the exponents, and it's well known. But what I want to stress that in the liquid state, there is no long-range order in the radial direction, and there is no long-range order in the angular direction in this case. Now let's jump to the fully solid state, which is a high-pressure amorphous solid. Here, when you do this inflation, you find that elasticity, classical elasticity theory works very well, and it predicts a displacement field that has a long-range order both in the radial and in the angular direction. The radial is simply because you have a power law decay. This is exponent, this is a power law. So in the long-log plot, this is straight, and this is like this. So in the solid, you have a power law decay with a long-range order, and because of we know that all the solutions for such an inflation problem in this geometry is yielding to so-called Michel solutions, which are well known, and they are angular sines and cosines. You have also angular long-range order. When you go to this phase here, which is in the middle, that you cannot avoid by reducing the pressure, you find that you break the angular symmetry, but you maintain a long-range order. Now, the long-range now is not in the power. The solutions are much more rich. There are Bessel functions. I'm not going to go into the detail, but what you find, this discovery of recent months, is that when you go from the phase, intermediate phase, towards the solid phase, and there is a divergence in the angular length, and this divergence is characterized with critical exponents, etc. for those who want to see more, in 2 dimensions, this has been published recently in Fields of Letters, and in 3 dimensions, it's now in press in PNAS. And the fact that there is a 3-dimensional such transition is rather surprising. The reason is that the transition is of the Kosterlitz-Thouless type. Just very quickly, Kosterlitz-Thouless type is a transition that was discovered in the XY model, in which vortices are produced at some temperature spontaneously, and this breaks very interesting symmetries, and it makes a topological phase, a topological transitions. This was awarded a Nobel Prize a few years ago to Kosterlitz and Thouless, but that can exist only in 2 dimensions. As I say, the Kosterlitz-Thouless transition, the hexatic transition, which is also similar, can exist only in 2 dimensions. The discovery that we have here, that the transition that I'm talking about within the jammed phase exists also in 3 dimensions. So this makes a little bit of noise and a little bit of excitement in the community. So thank you very much for your attention.
Thank you very much. Alessandro is from the École Polytechnique here at ULB, so he's from the Aerothermomechanics Laboratory. So please, the floor is yours.
Yeah. Okay. Thank you very much for the invitation. It's a pleasure to be here. So I'm going to start with a question for all of you. When you think about digital twins, what do you think, what comes to your mind? Maybe if we ask here at all the people here in the room, you will have several definitions, no worries. I looked at this paper, there are at least 112 definitions. So there is no problem. We will add a new one in this presentation. So I want to talk about the use of machine learning and digital twins to decarbonize hard-to-abate industries. These are industries that contribute a lot to our wealth, our way of life, and it's very urgent. I will try to convey to actually decarbonize them. Just we don't have to discuss too much about the need for decarbonizing. Here you see, I want just to maybe let you discover this this project by a Swedish photographer, Christian Aslund, a glacier comparison at Slowboard. And you see the effect. So after 100 years, the same picture in the same place, you clearly see the impact of climate change. When you talk about climate change, the next question and the next topic is always decarbonization. Now, decarbonization is, of course, a very important thing, but we usually focus on the easy task, which is decarbonizing electricity. What is more important and more difficult to do is to decarbonize heat, which is 50% of the energy use today. Now, decarbonizing heat is very complicated. If I paraphrase here George Orwell, all sectors are equal, but some are more equal than others when it comes to decarbonization needs, because these industries are very energy intensive. They require high temperature heat that you can only get today with fossil fuels. They also require very high density, the availability of on-demand energy sources that is not possible with alternative sources today. So it is by all means what I would define the elephant in the room of the energy transition. And it is a pressing issue also recognized by the International Energy Agency, because it is very challenging to think how these needs will be electrified in the near future. Now, in this context, what we focus on is a possible way to actually tackle this through the development of what we call renewable synthetic fuels. So the idea is that you use excess energy that is available at times where renewable energy is not needed to produce a variety of energy vectors. And you see they include molecules that are on everyone's mouth, so like hydrogen. Everyone talks about hydrogen. Some people talk about ammonia as an energy vector, energy carrier. But also if you have a biogenic source of CO2, you can also think about methane, methanol. The fantasy of the chemists is unlimited, and you can do whatever you want. But actually, the point is that once you have all these energy vectors, to actually produce heat and electricity on demand, you do need new technologies because you can produce all the synthetic fuels of your dreams. If you do not convert them properly, then you are at the same with the same problems as you began with. Okay, combustion, you might know, is a very complex process. First of all, it's turbulent in most of the times. Richard Feynman said this is the biggest unsolved problem in classical physics. If you add on top of that chemistry, you're not making things easier, for sure. There will be a lot of scales and processes that will interact with each other. And today, it's very difficult to anticipate how these new fuels that we are actually developing and using will have an impact on the structure, on the turbulence, the interactions with turbulence, on the emissions, the product quality, if you think about the sectors that I mentioned before. And so what we actually do in these problems is usually we can deal with them with diagnostics, but I don't know if you have ever been close to an industrial furnace. It's not the easiest place to be close by. It feels like being in hell, being on the earth. But the devices themselves will actually suffer this kind of environment, so you cannot deploy massive diagnostics in these environments. Same time, you might think I can do very complicated numerical simulations, but for the scale we are talking about, high-fidelity simulations are not even possible. You cannot today simulate with high precision what happens in a gas turbine of an airplane or for the production of energy. It's not possible. Okay, so what we do is that we actually try to leverage what we know about these things. So we have all the theory that is related to that, the power of machine learning methods, as well as the availability of data to develop these digital twins for very complex flows and for very complex systems. And the idea, and here you have another definition here for our digital twin, is really to actually bring together a multi-physics simulator that actually uses the best available models, information from sensors, input data that actually is able to somehow replicate what happens in a physical twin. But the key point here is to actually being able to do this in real time. We want to be able to actually predict what happens in a complex system in real time. We cannot afford waiting 6 months for a simulation to be performed. And so this is really the challenge that we have in front of us. Okay, so how do we do that? We combine different techniques. I will not go, of course, in the details to that, but we actually combine concepts from statistical analysis like dimensionality reduction, the development of reduced order models, leveraging the power of machine learning, and a simulation of heterogeneous data to bring all this into life. And you see here an example of this. We have actually applied this to systems of very different natures, from simple, you see on the left, a Lorentz attractor, and you see on the right a very complex furnace that you would find in the aluminum industry or in a glass industry. The idea is really to have the possibility to predict these systems very fast, to be able to actually capture the variation that could be related to a variable feed to the system. So in this case, on the right, you see what would happen in a furnace when you actually use a charge with the variable content of hydrogen. This is something that we will see for sure in the nearby future. And of course, this is possible. This combination of very fundamental and applied is possible through funding that comes from the European Commission, the European Research Council, the FNRS, and all the other possible means that we have. And I would like to finish here by just stating that in a time that where we actually hear the winds of war that actually come also in our universities, I think it's very important to remember. I really like this quote from Robert Schuman. It's very related to what we do. You see, in 1950, when the the basis of the current European Union were put. He remembered how tackling a societal challenge for the benefit of citizens and not for killing people would be a very good thing to do. And this is why we actually lived in 50 years of peace that we should always be grateful of. Thank you very much.
Thank you very much.
Yeah. Hello, everybody. Biologists on the bar now. So yes, I'll talk about energy, fuels. I'm a biologist. Yes. So you now understand my uncomfort zone, and then of course this is going to be quite of a talk that is sort of provocative, a little bit, but based on a lot of good data and research that we are doing at the University of Brussels. It's not also easy to talk about that because, you know, I have the whole group here with me today. So if I screw up something, they might just, you know, give me like a shake tomorrow, Monday, mostly. I'm using their data, so a big thanks to them first. What I will talk about today is going to be how we use light for accelerating reactions. In this particular case, how we can produce new kind of biofuels, so what we call fourth-generation biofuels. I want to start by giving you a number. Of course, I'm a biologist. Why don't you play with numbers? 67 million tons of gasoline. That's what we consume every year in Europe for fuel road. So let's say that these are the cars that are burning gasoline every year. So this is different from what Alessandro just presented. So this is let's say the light duty consumption. So this is something that we can do something about. So we can replace this fuel consumption because here we are just replacing something that is used by small car, not by heavy industries. And overall, the total toll is like around 240 millions because we have to also add diesel on top of this. But for the moment, we just focus on the gasoline, so the 67 million. When talking about the share of energy that we do use in Europe, we do have quite a clear picture that only a third belongs to sort of, say, European-made. The 2/3 are either from imported, let's say, fossil petroleum or natural gases, or let's say other kind of solids, let's say fuel, carbon. And so what we have left in Europe for our, let's say, scalability and to make, like, let's say, Europe less dependent from other kind of countries or systems are only the nuclear energy and the renewable energy. So those are the sources of energy that we could scale in Europe, but it's important to think that these should be done in a way that, although we might produce electricity, we should not use lithium for stocking this energy. So, no. Yep. So the only way that we can do and, let's say, make Europe less dependent from, let's say, other countries is to make like this transition lithium-free. Why I have to hammer on this aspect? Because lithium is only present in few countries in the world. Actually, it only relies on 2 countries, China, US, for the distribution. So if we're going to link the European economy to the batteries of lithium, we're pretty much going to close our, let's say, knock on our neck on only 2 realities. And so this is going to be, I think, like in this particular context of geopolitical transition, even more dangerous for Europe. So, and also bear in mind that many times we mine lithium for making new batteries, we are consuming a lot of CO2. We are emitting, a lot of CO2. So every time you see like an electrical vehicle, think about that. For making that car, it costs twice as much the CO2 in emission just for making it compared to a normal thermal vehicle. So you have to really drive your car for maybe 20, 30, 40 years before an electrical vehicle can become, let's say, equal to a thermal vehicle in terms of CO2 emission. So think about that. So as I said before, if you want to do this transition, consuming less petroleum, so importing less petroleum and replacing with something that is made in Europe, we have to focus on renewable energy and, of course, nuclear energy. I'm not a nuclear physicist, thanks. And then, I'm going to focus on the renewable energy part only. And so here you can see these are the 6 sources of renewable energy that we can exploit in Europe. 5 of them has one thing in common, that every time we produce this energy, they have to be distributed because they are not stockable, so that we cannot stock this energy. So they need to be connected to a grid, electrical grid, to be distributed. Instead, there is only one that can be, let's say, produced and then stocked in form of liquids, and so very well suited for replacing the needs of putting something of liquid in a car. And so that is the biofuels. So how do we produce biofuels in Europe or around the world? So in the last, let's say, decades, so let's say 40 years, we've been producing it with, let's say, first generation technology, something that is based on, let's say, starch or source of food. And so this is competing again for the food that people could consume, and instead is used for producing bioethanol. So this one created a lot of ethical burden and ethical problems. It has been, usually one of the arguments has been always used for flagging the biofuels as the bad one. But in the last 20 years, so we came across to a new technology, again, that is called the second or third generation biofuels, that is not taking at all anything that can be consumed and eaten by people. And so this is only touching the not digestible lignocellulose. So this is pretty much the same part of the plant that you create, you produce every time you have to produce the grain that you don't gonna eat, because this is what is called the straw, or in French, la tige, or yes, la paglia in Italian, let's say. And so this one contains the treasure. The treasure is the lignocellulose that is made a lot of cellulose and so sugar. And so the technology of the second generation, third generation is there to touch this kind of molecule, the cellulose or the lipids if it comes from algae, so to make it either bioalcohol, bioethanol, or biodiesel out of it. And then the last generation, the one that we focus in our lab, it is the one of combining the sunlight with a direct conversion of CO2 or gas or greenhouse gases into alcohol, so into biofuels, using actually enzymes and the energy of light. So I will explain you better this part later. So the technology that is now mature and then created, let's say, investigated in the last 20 years on the second generation technology, use the cooking as a, let's say, really hot water, under 50 degrees for a few minutes, just to convert the straw into that kind of, brown pulp. Yes, looks ugly. And then we learn from nature how to get enzymes. So you see there in a wood, you have always these mushrooms, these fungi that are degrading lignocellulose. We learn from that how they do it. So we kind of copy their technology. We extract the enzymes. If you are more on the 80s style, let's say that the enzymes are sort of Pac-Man, they can degrade polymers. In this particular case, they are very good at degrading cellulose to make sugar. So the transition from that blob of a, let's say, brownish pulp into something that we can ferment for making bioalcohol looks like that. So we haven't added nothing than just simple the enzyme in that, let's say, reaction. You see there's a lot of water already present there. As soon as we add the enzymes, it becomes liquid and so pumpable and so fermentable. So now, after just adding a little bit of yeast, the same yeast that you use at home for making pizza or the brewing here in Belgium, the beer, you can obtain your wanted bioalcohol. In this particular case, it's ethanol. And so now this ethanol, after the, let's say, distillation, can be used to replace the petrol fuel in the car. And so the actual pool of car that we have in Europe, they are all sort of, able to tolerate quite a lot amount of ethanol. With a little modification, you can even add 100% of this alcohol. In my lab, what we do, we want to move forward. So we want to accelerate even more this reaction of the enzymes, and we want to do it with the energy of light. So in this case, we can really reduce even more what is the consumption of energy, and so the environmental efficiency. So the idea was to combine the light that comes from the sun, or even from, let's say, an electrical bulb, doesn't matter, as long as it's paid back. And then to photoexcite a photosensitizer. This photosensitizer is a pigment. You all know what is it, chlorophyll. It's the one that makes the plant green, sort of say. And so this one is able to photoexcite and shoot electrons. And so our job is to grasp this electron and then to give it to the enzymes so that they can run their own reaction in a faster way. And so we decided to combine this with two particular enzymes. One that is a methane monoxygenase. This enzyme is quite fantastic, so to say, but super hard to work with. So this enzyme is able to capture the gas. So I don't know if you heard about the methane. It is actually the most polluting gas, not the CO2. So it has 14 times the greenhouse gas potential than CO2. So every time you look at the atmosphere, you think about CO2, yes, fine, that's the bad guy, but also methane, it's 14 times that as bad. So the good thing is that now we have an enzyme that can recognize and take the atmospheric methane and then convert into methanol with an oxidation. This is happening at room temperature. And so we can pretty much run this reaction in, let's say, mild condition, if accelerated by light. So now the work that we are doing in our lab is to find the condition for making this reaction happening in a yield so that we can keep running and then extract as much as possible methanol out of the methane. The other condition is that,
David, 1 more minute.
1 more minute, yes. So it's one of the other projects that we are doing. So we're accelerating the reaction of these enzymes that are also degrading lignocellulose, so to make new products. I say this is a technology that is scalable, so it is mature. So these are the 3 implants that are, let's say, producing today biofuels of second generation. I want to make stressing the point that one is Italian, so is in Crescentino Tortona. So that's been one of the first being produced in the 2013. So now they are up running and producing alcohol and biofuels. How much straw do we have? Can we cover all our needs? Yes. So we have something like 500 million tons of wheat straw. Out of this, are the best of the technology that we have today, at the state of the art of technology, we can produce up to 90 million tons of fuel. So this is enough to completely replace all the gasoline that we consume in Europe. And all those straw is made in Europe. So in the last 20 years, we learned how to harness this technology. The biofuels was not only the end, was actually the entire journey. Doing this kind of journey, we learned many things. We learned how to make out of this biomass many different products. As you can see, biocomposites, transparent wood, bioplastics, skincare. And then one of our favorites, let's say, application in my lab, we are making plant vaccine. So we are taking this part of molecules, sugars, give it back to plants, and plants can recognize as an immune stimulator, and so making the plants more resistant towards pathogen. Wonderful plot twist, let's say, from biofuels to plant vaccine using the same technology. So this is what is now today the biorefinery, and then we are working to make it joining these 2 important sectors of Europe. Yeah, so you have much more to read. You can go to the Circular Bioeconomy Europe portal, where it is now the entire industry of bio-based industry, let's say, represented, more than 1,000 company today. So it was not just like a mere goal to produce biofuels, but was to create a movement. And then Europe succeeded on that. Yeah, so these are the conclusions, but you can read it and are the same things I just said. Thank you.
Thanks, David. And I see the chat is online. So in the chat, can you put on your slides? Because we see finally your face.
Okay, very good. So it's
this is good.
An improvement with respect to what we had before. So I should be now. You should be able to see the slides. I hope so, at least.
That's perfect. Okay, so you have 10 minutes.
Okay, thank you for the introduction, and thanks to the technician that at the end helped me solve the problem with the good old log out and log back in again. It always works. So today, this afternoon, I'm going to talk about half of the work I do. That's about biophysics, computational biophysics, so molecular recognition in plants. The other half usually involves graph algorithms, complex networks, complex systems, maybe will be for some other time. So the story here starts with auxin, which is the most important plant growth hormone, and its receptor tier 1. That's a protein that you see here on the screen, represented in ribbon representation for most of it, and in surface representation at the binding site, where inside it you can start seeing this little molecule, as I mentioned, it's called auxin. Now, if we zoom in the pocket, you see that you have auxin at the center, and that this pocket, this binding site, is not a shallow indentation on the surface of the molecule, but rather it is actually a deep crevice. In fact, from the residue on the top to the one on the bottom, from the red to the blue, it's about 15 angstroms of distance, which on atomic scales is quite a distance. So why is this something that we started looking at? This is how I started really working in this field, in this topic. That's because if you look at the structure of auxin, which is the one you see on the left, this is incredibly similar to the one of the amino acid tryptophan, one of the essential amino acids, which is the one that you see on the right. This is not by chance. This happens because inside the plant cell, auxin is synthesized starting from tryptophan. However, if you try to do an experiment and see whether tryptophan binds tier 1, you will find that the answer is no. Auxin does, tryptophan doesn't. Hence the question, how does this receptor, how does this molecule, tier 1, this protein, recognize that auxin is good and it wants it to bind and tryptophan isn't? What is the difference? What are the interactions that allow this distinction? So in order to answer this question, we started doing what basically everyone else will do. Let's do molecular docking. That's a classic bioinformatic technique. And if you dock IAA, IAA is the acronym for auxin, it stands for indole acetic acid, you get the results you see on the left. It's kind of like pretty good. It says like, it should bind at the bottom of this pocket. And in fact, if you crystallize the protein with IAA, you will find the results in the center, which are effectively identical. That is great. But then if you try to dock tryptophan, you find the results on the right, which is a very plausible pose as well. So this will suggest that tryptophan is also a binder, but we know experimentally that that is not the case. So we said, all right, how do we find the reason why? And we came up with something that we call tomographic docking, or tomodoc in short. The idea is basically the same as when you do a CAT scan, if God forbid you had an accident or something and people want to, instead of doing a normal X-ray, the doctors may want to do something that will be able to allow them to see inside you in 3D. So the idea is the same. We basically do slice by slice and we try to figure out how the molecule moves as it descends or tries to descend the whole depth of the pocket. So we say, okay, how about we try various different molecules and see what the predictions are? So we tried several of them, 6, you see them here on the screen. On the top row, 1-NAA, 2,4-D, and IPA. On the bottom row, ICA, IBA, and IDA. And based on the poses they adopt, the interactions they do, etc., we predicted that the ones in the top row would be binders and the ones in the bottom row wouldn't. So, of course, in order to verify this, we went to the lab. And in the lab, we found what you see over here. We used first SPR, surface plasmon resonance, is a physics-based technique, and then we did experiments on the whole plant, so that's the 2 experiments in the bottom row, and you actually find exactly the same as predicted by tomodoc. So this would even allow us to do a kind of reconstruction of the pathway of binding, even though this reconstruction wouldn't be really super precise because we are still talking about something that inherently is a molecular docking. We wanted to understand the mechanisms of this, behind this, so we said, okay, let's go with the heavier artillery, that is molecular dynamics simulation. Let's simulate absolutely everything. Atom by atom, we write down the Lagrangians, we crank numbers and see what we find. So to make a longer story short, we find that the molecule by itself, tier 1 by itself, closes its binding pocket, but if we simulate it then with the addition of auxin connects, makes a salt bridge with that arginine that is in blue there on the screen, and then it moves it away. I say that it looks like lifting the lid off a pot, reopens the pocket, and then eventually can descend down. At this point, we wanted to understand this descent, and skipping a few key passages that can't really talk about for lack of time, the final idea here was to use a method called the nudged elastic band. That is effectively something like creating many replicas of the system, and you keep the initial one and the final one static, and then you connect each replica with its neighbors via some harmonic potentials, atom by atom, that are the ones represented here by the springs. This is kind of like a sketch that I'm showing you over here. Then you let the system evolve, and the result is that you can observe by looking at one replica and then the next, and then the next, and then the next from the beginning to the end, what is really the pathway of least, the path of least energy that a molecule can go through during its descent. You're seeing it right here right now on your screens. This is really the same movie done 3 times in different representation to show you how it looks like. This is auxin that moves down, gets first bound on the initial arginine, then on the second one, and then eventually gets all the way to the bottom. And it should be happening in a few moments right now. This technique allowed us not only to find, to find what was this path of least resistance, so to speak, but also to identify what the most important residues were and their contribution, the contribution of their interactions to the binding energy and to the general free energy of the system, which is what you see on the screens right now. But that's only part of it, because as I said, this is multiple scales. At the yet bigger scale, what happens after this complex is formed is that a third partner comes on top. This third partner is one molecule of a whole family of proteins called oxIAAs that bind onto the complex between tier 1 and auxin via this dagron that you see here in purple, represented there in purple. There's many interesting things about this dagron. No time to talk about them now, but I'll say a few of them. The main one is that these oxIAA molecules, proteins, were not entirely known for what concerns the structure. This is because half of them is well-folded, but the first half, the one that binds onto the complex, wasn't solved. And it wasn't solved because these molecules are intrinsically disordered. We said, okay, fine. Can we simulate that? Can we try to do something? The answer is yes, but it turns out to be fairly difficult. In fact, if you even try with kind of advanced methods like DMP-fold, you may have heard of it, AlphaFold, you may have heard of that too, these methods fail. They fail pretty badly because effectively at the end of the day, these are statistical methods and no one had ever observed something like oxIAAs. So you can't really extrapolate to something that you don't know, that you have never seen, something that you already know. In fact, the results will be the ones you see on the screen right now. It will suggest that the whole first half of the molecule looks like a long spaghetto, which is not really the case. We knew that this wasn't the case from lab experiments. So we said, can we invent something that will go beyond these problems? And we ended up actually doing exactly this. So we thought of applying the so-called replica trick or replica method, but applying it to a generalized version of a stochastic differential equation, namely the Langevin equation, and modified in a way to boost some specific movements of entire domains of the proteins. This way, we could actually explore the space spanned by this protein, the first half, the second half is known, and estimate basically what its conformation is, if it's really a long spaghetti or not. The answer is it isn't. The answer is this disorder is an ensemble effect that comes from the coexistence of several folded structure, which two of them form about 91% of all the possible conformations, and then the other are basically transients. And this allowed us to see them, in a sense, for the moment in silico, but I'll say a couple of words later, and in fact simulate them. You see here oxIAA number 17 in pink, that this is results of a simulation, that is slowly getting close to the complex tier 1 and auxin, and eventually in a few moments you will see the diagram snapping in place and effectively connecting the two. There you go, the two proteins are there. So being able to do this, then we took these first two, the two main conformations, and we simulated them for a very long time, like microsecond level simulation, because we wanted to study what their contacts were, which residues are important for their interactions. And this is what you are seeing now in this movie on your screens. I don't remember which of the two is number 1 and which of the two is number 2. They account for about 50% each. You see there are very strong similarities, obviously, in the region of binding auxin, but there are also very, very important differences in the rest.
Sharon, one more minute.
Perfect. All the contacts. So we verified this in the lab using circular dichirism and NMR, nuclear magnetic resonance, and we found that it's exactly the numbers that came from the experiments were exactly what we predicted. This effectively has given us a new outlook on intrinsic disorder that accounts for 40% of all known proteins. This is not the end of the story, though, because we also simulated the structure of efflux carriers of this hormone. This that you see here is called PIN2, is their main efflux carrier. We made this model because the protein was not solved, was not crystallized, and structure not solved yet. This is a plasma transmembrane protein, a lot of transmembrane helices, which are here in surface representation in a very, very long loop of about 660 residues that is inside the cytoplasm. And this model actually was confirmed by experiments after the PIN2 was crystallized and the structure solved. And it was instrumental in discovering and understanding that the functioning of this efflux carrier is actually that of a multimer, not just a monomer. Going to a yet larger and more comprehensive scale, one last result that I'd like to mention is that we discovered the existence of a dicer argonaut mechanism also in plants. Up to this point, it was believed that this mechanism only existed in mammalians, but actually no, we found out that it exists in plants as well, and it is responsible for protecting the male genome, the genome of the male plants, from the damage that is caused by heat stress, such as, unfortunately, it's becoming more and more common due to global warming. The mechanism is based on a change of phosphorylation state in this argonaut protein. This is what you just saw. You may have noticed that the colors that represent the surface charge are different. One of them can recruit both helices of a microRNA, the other only one. Because of this, the effect is to bring back control.
I would really ask you to go to the conclusions. Thanks.
These were the conclusions on a deregulated genome, thanks to some retrotransposons and other transposable elements. And as I said, these were indeed the conclusions. So thank you for your attention.
Thank you again for this kind invitation to present at this conference with such distinguished speakers and colleagues. My presentation is a mix between European policy and Italian science, let's say. The title is, as you see, Laser Photoacoustic Spectroscopy for Fast and Contactless Sensing of Nerve Gases. This research has been performed inside the frame of the European Defence Fund. Actually, I am working at DG DEFIS. DG DEFIS is implementing. DEFIS is the General Directorate about defense industry and space. So I'm working in implementing EDF, European Defence Fund. I will not describe all these slides. The presentation is public. I authorize the organizer to share the presentation. Just to this slide just show you that there is a ramp up of European interest in defense. Of course, to maintain peace, not to make war, but unfortunately, we have also not to be naive, and we have also to deter possible attackers of our union. And if you are interested in such a kind of funding, I leave here for you this slide that emphasizes how an EDF cycle, EDF project will develop during time. So you start from the application and you end with the realization of the project and the final approval by the European Commission of the results given by the project. There are many categories, and I am more, let's say, involved in the biomedical response and medical countermeasures and CBRN detection, chemical, biological, radiological, and nuclear threats. And you will see that the project I'm talking about is exactly about CBRN. And EDF started to granting money, to granting funding in 2021, and now I'm participating in the writing of the topic text of 2026, and the 2025 grants have been awarded in April 30. So now I'll come to the core of my presentation, Mosaic project. Mosaic project has been funded by the European Union. In 2023, I was responsible for Enea of this project. And this project is led by the SAFE Foundation. So it is a story of Italian excellence because also the SAFE Foundation is Italian. And Enea, as you know, is a relevant institute, public institute of research in Italy. Here you can see the picture of the autonomous vehicle, the ground vehicle, where the detector, the chemical detector, is installed. Up to 2023, I was responsible of the realization of this chemical detector, and it is based on laser photoacoustic absorption spectroscopy. We have talked about today on planet detection and atmosphere of planets, but the principle is not that different. You irradiate a sample inside a cell, and you irradiate it with the laser, and the power of this laser is modulated at an acoustic frequency. Then the sample absorbs this radiation, and after the absorption, you have the development of heat and the emission of a pressure wave. And you listen exactly to the detector. Of course, your detector is very sensitive, but anyway, you are able to, with a microphone, to detect the absorption, the spectroscopic absorption of the sample. And usually this is performed in the infrared with spatial lasers. In our case, we use the quantum cascade laser. The important point is that you do not have contact between the sample and the sensor, and you can really imagine in the future to make a standoff detection of, let's say, dangerous substances. This is a picture of the first system. I will not go into details. I leave for you the presentation. But in a nutshell, the core of the system is a quantum cascade laser. And the picture shows the first prototype we developed. It is on a cart. So it's 1.5 meter high and 1 meter width. So it's portable in the sense that you can move. You can see here it has some wheels, but as you will see, we developed a smaller prototype that now is mounted on the UGV for ground operation, even in battlefields. Here I can show you. I go directly to the results. The idea is that you are in the battlefield or in a zone where you had a chemical attack, and probably by nerve agents, and you have the typical small discs of paper that you use to smear surfaces. So the robot goes there with a articulated arm, and it touches the surfaces, and in this way, you know that the nerve agents are quite heavy, so they, especially if the temperature is low, they deposit on the surfaces. So you smear the surfaces and you put the disc inside the cell, then you fire with the laser inside the cell, and in few seconds, you get the spectrum of the substance. And we tried some samples. One is with the water. One is with the DMMP. DMMP is a substance simulating a nerve agent in the different concentrations. So you see here, we had the DMMP of 3,000 nanoliter of DMMP deposited in the paper, 330 and 3 nanoliter of DMMP, and also the paper without any substance. And we measured 10 spectra per each samples in the mid-infrared from 7 to 8.5 microns with a resolution of 0.03 microns So it means 51 wavelengths, and the measurement time is 1 second per wavelength. So you obtain a spectrum in 51 seconds. This is quite fast. Then we applied the machine learning technique, a sort of artificial intelligence. And here you can see the results with the PCA. And it is clear the discrimination that the PCA gives. So each sample is clearly discriminated. Then we applied a predictive model, a PLS partially square model, and we were able to arrive to a limit of detection of 1 nanoliter of nerve agent simulant in the paper disk. Okay, now I'm already to the conclusion. I hope to be, I have been maybe faster than 10 minutes, so we can have more interval later. The present system, as you can see, it is a smaller. The actual team in Italy, the colleagues that are working now at Enea in Frascati are, as you can see, Antonella Lai, principal investigator for Enea, of course, coordinated but by the SAFE Foundation still, Fabio Polastrone, Isabella Giardina, Massimo Francucci, Marcello Nuvoli, Claudio Cicceroni. We are still in contact, but I cannot work for this because now I am seconded at the DEFIS, and I cannot nor supervise this project because of a conflict of interest, but they keep me updated on what's going on, and I'm very happy to be in contact with them. They are very good colleagues and friends. Just let me say just one word. I'm also representing here CLENAD Italia, and I give you the greetings of our directive board. As you know, CLENAD is a committee of the seconded national experts. We have an international committee and also an Italian committee. And as you may imagine, many SNEs, many seconded national experts here at the European institutions are researchers. This stated, I thank you again for your attention. Thank you.
Thanks again, Luca, for your intervention. And now we have the next speaker, who is Elio Tucci from the Université de Namur here in Belgium, Faculty of Computer Science. Elio is with us, so we will just wait that the slides will be fine. Okay. Perfect. And Elio, could you switch the mic on your left on? Thanks. So you have 10 minutes.
Hello, can you hear me? Okay, great. Great, thank you very much. My name is Elio Tucci. I'm at the University of Namur in the Faculty of Computer Science. And obviously, I thank you, the organizer, for inviting me here today. And I would like to show you, to illustrate you very briefly the activity of the BABOTS project, where we design and control small swarming biological animal robots. This is a EU-funded project that started in October 23 and will run until September 27. These are the partner of the project. So we have the University of Namur, and we have the Italian National Research Council. We have a company, the Zero Farming, also from Italy, and then we have the Hebrew University of Jerusalem, two institutes from the Max Planck, and a partner from the University of Aalto. And these are the faces of all the PIs involved in the activity of the project. So what is the BABOTS project? the main objective of the project is designing and building biological animal robots. And here you see the acronym biological animal robots is derived from BABOTS, is derived from these terms. What are BABOTS? BABOTS are organisms, animals, whose behavior is reprogrammed through modification of their neural system through genetic modification. So through genetic modification, we restructure the brain of this organism and we change their behavior. Currently, in the BABOTS project, we are working with a model organism in biology, which is C. elegans. Why we are working with C. elegans? C. elegans is a nematode, is a 1 millimeter round worm, which in the hermaphrodite condition has exactly 302 neurons, which are fully mapped. The map is known as connectome. So we know exactly how the neurons are connected, and we know a lot about the functions and some of the the function of the neural circuits. On top of, so this activity of designing and building BABOTS, we also try to study collective behavior, because you will see that one of the main point in the project is to engineer collective behavior in the BABOTS. And we also look at other issues like biocontainment and also all the ethical aspects related to the design of BABOTS. Now, compared to classic electromechanical robots, obviously BABOTS, they produce themselves and they are fully degradable, so they don't require fabrication and they don't generate waste. In terms of dexterity, obviously they are very small and they're very sensitive and very agile, which is not always the case with classic electromechanical robots. However, robots can be programmed, and BABOTS are organisms, so they are autonomous system. And what we are trying to do is to develop a technology to let this worm to work for us. Now, the final results of the project will be the bacteria killing scenario. In this scenario, a group of BABOTS should detect a pathogen, which is a bacteria. They should crawl first to places where they can find bacteriophages, so viruses that kill the bacteria. And then once they're infected, they move to the source of bacteria and they kill the bacteria by infecting them. This scenario requires a series of collective responses like aggregation, swarming, and collective decision making, which are not part of the natural behavioral repertoire of the worm. So these are the behaviors that we want to engineer. The scenario, you should imagine the scenario like this. So the scenario will be in a petri dish. The BABOTS will be placed on a food source. Then as soon as they detect the presence of the invading pathogen, they crawl to the place where there is the bacteriophage. And then once infected, these bacteriophage, they're not deleterious for them, but then they move towards the crawl to the pathogen, and they infect them and they kill them, freeing the place from the invaders. This is what we would like to generate at the end of the project. This will be the final demonstrator. To achieve this bacteria killing scenario, we are carrying out an interdisciplinary research plan, where obviously there is a huge component from the synthetic biology, where we build the behavioral building blocks where we do the genetic modifications and we generate the behaviors necessary to let the worm to work for us to execute the scenario. But we also study the worm in a natural setting. So we do some studies in animal behavior, and we do lots of modeling to test in a quick way hypotheses concerning the mechanisms underlying the collective behavior, which is obviously an emergent property of the system. And we also look at ethical aspects. I will mention vertical farming later on. So just to give you an idea of the kind of things we are doing in synthetic biology, obviously this is a very complex part, at least complex for me, because I'm not from the field. One of the things that we are doing, we have done this pheromone-based aggregation. So in this case, we are taking advantage of a chemical signal. So this is particularly sex pheromone released by the hermaphrodite to attract male when with age they run out of sperm. So what we have done, we have modified, so basically the hermaphrodite, they're not able to sense and to react to this pheromone. So what we have done, we have modified the neural and sensory apparatus to make the hermaphrodite sensitive to this pheromone, and so they can attract each other. We have done other things, for example, the switching mechanism. These are other circuits that allow the swarm to move back and forth between two sources of other chemical signals by engineering some neural circuits that modulate the concentration of calcium in the brain of the worm. In the animal behavior domain, so basically most of the work in the synthetic biology is mainly done by the...
One more minute.
Okay. The Hebrew University of Jerusalem and the Max Planck. In the animal behavior, we are mainly working in trying to see whether the group of worm can climb another gradient better than a single worm. And we also build the odor chamber that you see here in the movie. In the modeling part, we are using lots of different tools. We have a kind of toolkit to explore different hypotheses concerning the mechanism underlying the collective behavior. And we are exploring lots of issues related to the ethical aspects. We call it ethicality of babots. And as far as vertical farming, we are one of the ideas is to test the babots in a natural environment, not completely natural environment, but in the vertical farming type of environment where we can control the environment 100%. If you want to know more about the project, I invite you to visit to email us or to visit our webpage, where you will also find these statements which emphasize the fact that we are committed to use science for peace, for a fair society. Thank you very much.
Thanks, Elio, for a talk. And now we go to Simone Lucatello, who will join us online, I guess, from Mexico. Is working at the National Council of Science and Technology, Mexico. Is a coordinator leader report for GEO7 of the United Nations Program and Environment.
Yeah, thank you. Thank you very much.
Okay.
Good morning.
We see your slides. Perfect.
Can you hear me? Yeah, thank you.
Sure.
Good morning.
Yeah.
Hi, good morning once again from Mexico City. I'll stop the video so you can just focus on the slides. Thank you very much. Thank you again for the organizers, and I'd like to draw your attention today on one of the research projects that we recently finished after 5 years of work in Mexico, funded by the European Union with more than 60 institutions worldwide, and some of them were from Italy, and as an Italian, I was coordinating part of the project here in Mexico City at my institution where I work. And the title is Digital Transformation and Sustainable Development, the Prodigies Project. So what is Prodigies? This is the acronym. This is a project that was looking at the digitalization impacts in different ways, not only artificial intelligence, but all has to do with technologies, ICT, IT, and so on, and how it is related to sustainable development, and how, you know, between Europe and other emerging powers around the world, we are working to combine those things and see how technology is having, you know, what kind of impact it's having. So about this project, it was again funded by the Horizon 2020, and it has several goals. As I mentioned, is exploring digitalization, sustainability, building a research network, cooperation, strengthening the science policy interface, supporting capacity building, knowledge change, and of course looking at, you know, the sustainability issue, not only economic or social, but also environmental. And we try also to look at, you know, also identifying risk, opportunity, solution for this digital transformation process and where it is going. So one of the main line of research which I'm dealing with, I was also in charge of, you know, for the 5 years of all this project, was looking at really what is the ecologically and environmental footprint that we're having with digitalization. And of course, I'd like very briefly to share with you some of the results. And everything can also be found in the webpage of the project. At the end, I will show you. So just a very, very brief overview. I don't have time to go through this. Also, my presentation will be public. You could check it. But just to give you an idea, the digital carbon footprint is quite a lot. We are contributing around 4% of the greenhouse gases emissions. And it has a very clear impact on climate change, especially for the energy consumption and energy pollution. We are also, you know, there are several numbers that can draw your attention, but I move to the next one. Maybe this is easier to understand. As you know, we are, you know, growing in population. It's just not the latest data, but we are a lot of people, and we are, the average is about 5.351 billion population using a mobile phone, and every mobile phone has a capacity, as you know, of polluting and having an impact on the environment, not only in terms of production of carbon emissions, but also for the use of materials that is done, and raw materials and other things that rare earth materials and things that we'll be looking at in a few minutes. And then, of course, we have a lot of population which is connected, and the social media, which are playing now a huge role in the issue of emissions and environmental footprint. So why does it matter to look at, you know, why we do care much about the environment? We have only one planet, as we know, and why it is important to focus on the benefits and the trade-offs of this digitalization. We know that it is not a neutral process for the environment. It's really transforming not only society, but all the ecosystems, and all is happening, you know, with nature providing us the benefits for the growth of the planet. So we need to understand much better this relation between material, the energy costs, and we know that there are, of course, positive sides. We know, I would say 80% of the interest of the research is looking at the benefits, but we know that there are harmful potential. It's really to be done. And again, one of these processes want to shed the light on what is happening. So in terms of other footprints, as I mentioned, one of the key issues that we are looking at, North America, actually where I am, including of course Canada, US and Mexico, is the area of the world where data center is growing in a pace. In the last 2 years, there has been a kind of 5 times, 6 times the number of data centers that we had, you know, at the beginning of the process of digitalization is mushrooming basically all over North America. And this is associated also not only the creation of waste, but also the use again of e-waste, as we call it. And the training of large AI models, for example, is emitting so much CO2 that is equivalent probably to more than or plus 5 cars, medium cars, equivalent of all emissions. So what are where these minor environmental impacts are going to? So the energy use we mentioned, resource extraction, lithium, cobalt, the rare earth materials, e-waste, toxic disposal, and emission from hardware and production and use. Just a very brief overview about some of them. Extractive mining, this is really crucial. It is not only happening in Europe, but it's happening in all these global south countries that we've been looking at. And it, again, in a huge and intrusive and significant source of pollution, not only in terms of extraction, but also, as you know, to clean lithium, for example, or to clean some of the earth material for phone. It's really looking into murky manufacturing and traders issues. And this is, like, remember, is something would happen with diamonds or other things. So we have to look at these long distance effects that we may have in the use of materials. The other one is about the cryptocurrency and the blockchain. As a ledger technologies, we know that this has been also working quite a lot in the, especially in the issue of the digital content, the supply chains, and what is happening with the ecological footprint of the blockchain. This is mostly in the network. This is another dimension. Is about what is happening also with the use of satellites. Just think about what, for example, SpaceLink is doing, which is launching about 150 satellites every 3 or 4 months. So we are really looking also with the United Nations at what can be happened with the Outer Space Conference for international law of the space, and see what is it really can happen in in the near future. But you can clearly see on the right side, probably in this cartoon, what may happen in the future. This also we're having in the exospace a lot of accidents already. And then finally, just to draw your attention, we all use phone, maybe one more on the phone. 80% of that is done by rare earth materials, and it is important to remember that also have a cost when we look at all of them and the time we extract materials. Finally, I'd like to talk about what is, we are thinking to go after these projects, that we are already in touch with the Copernicus and looking at what is happening with the digital breach and the security nexus, because the amount of satellites information is produced also used for attacks, for breaching national security, and also for surveillance, and also for, in democratic or non-democratic countries is being used as a tool, and we want you also to draw some of the attention over there. I'm not talking about the case of the example, but we have plenty of cases in Indonesia, Brazil, in Mexico, and South Africa. In Europe is Eastern Europe mostly, but also some of the other countries in Europe. Just to finish, what can be done and some final thoughts. Just remember, this digitalization process is not sustainable per se. We need to look beyond and see what do we mean with all this implication, and we have to build an environmental responsible transformation, where also equity and justice and other issue ethics also should be brought in. Just one final concept for you to take away. We are working on this one. It is quite new. It's very interesting. It has about the idea of data pollution, not only in terms of what data can do through the computers or through the network that are available, but also the emissions that are leaked into the digital system, disrupting, institution and public interest. That's why we was talking about security breach. So it's very interesting, and this is something that we've been looking at this project, and we will be able to publish something soon in a paper and in a collective book funded by the European Commission. So thank you very much, and I remain available for any question. Thanks a lot to all of you.
Thanks, Simone. Thanks for keeping your presentation indeed within the 10 minutes limit. We go to the last speaker of this session, which is Angelo Pinto. He's an IEEE Fellow, Vice President of External Manufacturing Production at Intel, San Diego, California. And I don't see yet I see you, but I don't see yet your slides. Could you unmute? Yeah, there we go. Perfect. Okay. Angelo, do you hear us?
Yes, I do. Do you see my presentation?
Not yet, but finally we see you.
I am sharing my video, my screen. Let me try one more time.
Sure.
So you say connecting. Oh, I see. Okay, share, it should work now. Can you see my screen?
I think it's coming. Yes, perfect.
All right.
Okay.
Yeah, so good morning, good afternoon, and good morning, everyone. My name is Angelo Pinto. I live in San Diego, California. I'm calling from Texas today. I'd like to extend my gratitude to the organizing committee and the STEM moderator, Dr. Napolitano, for providing me with the opportunity to share my journey in the semiconductor industry. I have been impressed in listening all these research, quality research, relevant research, prestigious research, and the fact that I can help with high performance computing, it giving me a sense of purpose. And my journey started with a PhD in solid state physics from the University of Catania, Sicily, and leading to my current position at Intel, where I manage the manufacturing of most advanced semiconductor chips. Moving to the next slide. So I'd like to start this presentation with the semiconductor. Let me see if I can use a pointer here. With the semiconductor megatrend.
Angelo, we're still looking at slide number 1, in case you have changed it.
Yeah, I'm in slide number 2.
Wait. Either you try full screen or you try to scroll on the left bar.
So I don't know what is happening. Maybe I can stop sharing, start over again. Do you still see my screen?
Not at the moment.
Okay, so let me screen share. Does it work now?
Yes, we see slide number 2 at the moment.
Yep. Okay, slide number 2. So the semiconductor megatrend. The semiconductor industry is poised to be a key driver of the global economy, as you can see on the left graph. Projected revenue are expected to surpass $1 trillion by 2030, and this growth will bolster the broader electrical engineering, information technology, and they all will contribute for 10% of the global GDP, which is expected in the range of $145 trillion. When we look at the revenue breakdown by product platform, high performance computing, mobile and automotive will account for 80% of the projected revenue. And these sectors are significantly influenced by the rise of AI, making the latest in a series of innovation waves over the past 40 years. Innovation, the first innovation wave, the PC in the 90s, followed by the internet 2000, smartphone 2010, and then the cloud in 2020, and then after the COVID, the incredible acceleration of AI in the last few years. My personal contribution over the 30 years of my career, I had the opportunity to contribute mostly to the telecommunication and mobile smartphone contribution coming in the field of process integration, device engineering, and manufacturing. And recently, I had the opportunity to work on APC and developing the most advanced chip for AI PC. So I hope you can see the next slide.
We're still at slide number 2.
Oh, okay. So I think we have This is a big issue. You don't see change in the slide.
No, we're still the same as before. Slide number 2.
Okay, so I don't know what to do. I may have to. Okay. I don't know what is happening.
We just see number 3 at the moment. No,
no, number 3.
There was number 3 before switching off the screen.
Okay, so it was a changing page.
At the very end, we saw slide number 3.
Okay, so I need to be patient. All right, number 3. So AI will spark an exponential economic growth. And in fact, an AI-infused world is emerging with a widespread of application into our daily life. And a fascinating projection from Cathie Wood in a TED talk, 40% compound annual growth rate in equity market capitalization by 2030. And that will be driven by basically 5 disruptive transformative innovation. The public blockchain, the multi-omic sequencing in healthcare, energy storage, robotic will be surrounded by autonomous taxi, but all they have in common is, again, AI. So the common denominator of all these innovation is back the semiconductor. So hopefully you can see the next slide.
We're not seeing your slides at the moment, but I guess the technical issue is not going to be solved easily. So I would ask you just to continue until concluding within a reasonable time.
Okay, so can you see the slide now?
Nothing at the moment.
Okay. All right. So AI thrived at the intersection of 3 major innovation. The neural network, so the neural network, the GPU accelerator, and the internet data. But let's start a little bit from the AI. So the AI domain, it's again is focused on developing system with intelligence behavior. The machine learning is a subset, which the goal is to learn from data, identify pattern, and making decisions. Deep learning is a machine learning technique leveraging on neural network, and natural language processing is an application based on human language. But the acceleration of AI in the last 3 years has to do with the intersection of these 3 innovations that will become available. The neural network, it was available already in the 90s, but it was limited by the CPU capability. And in this neural network, nodes and connection constitute a model which emulate our brain with neurons and synapses. And a model allow to predict the Y given the X. For instance, given a picture, we can predict the probability that the picture represents a dog or a cat. But what is important in this to supervise the training of a model, the learning is really recaptured and stored in this W and B from looking from a mathematical viewpoint. And this brings to the next acceleration. The GPU have been able to, with massive parallel computing of basically a sum of product, will allow to, again, from the Y and the X to be able to extract the learning through the W and the B. So at the end, you need the X and Y. So you need the data to train the model, and the internet was the next component. Can you see this slide?
No, we cannot see the slides.
Okay. So the common denominator of the semiconductor is transistor. And, so here I'm showing the Intel roadmap on transistor technology. Sorry. So, transistor roadmap that has allowed us to scale the transistor footprint. So the latest technology have a minimum geometrical features in the range of a few nanometers. So pretty much we can pack hundreds of transistor in the same dimension of influenza virus. And I think what was interesting is all the semiconductor was driven by the Moore law, which expect that every 2 years we will be able to scale the dimension of transistor by 2x, or in the same area pack 2x more transistor. But all of this has been changed with AI, establishing even a faster pace. Now the scaling of transistor is no longer enough because the key driving force is the training compute power, which is expected to increase 16 times per year, and that require to leverage on 3D packaging, where many chips are stacked on top of each other. Each of these chips has 100 billion of transistors, and altogether a system on package can be in the range of trillions transistor. And also the semiconductor industry has changed from the beginning, where we have integrated design and manufacturing. We are now evolving, decoupling design from manufacturing. So we have a company called the Fabless, specialized on design, and company the Foundry, specialized on the manufacturing. A manufacturing module now is in the cost of $15 billion. So this decoupling has given a big acceleration to innovation, because allow people to focus on the design of a chip, which is not the capital intense, and other company to focus on the manufacturing.
Angelo, I'm really sorry for the technical issues, but here we are running out of time, so I would kindly ask to go to the conclusions.
So yeah, the conclusion is that I have the privilege in my career to contributing to the semiconductor industry from contribution in telecommunication, mobile, and recently on AI PC. Yeah, thank you.